Hello students, today we will look about the quantitative principles of computer design. That is, we are focusing on the various guidelines and principles that are useful in the design and analysis of computers. So when we add some enhancement to the new system that is to be generated, what are the different things to be considered and what are the different principles behind the design of a new system. So earlier sessions we were considering the factors to be considered for evaluation or comparison between already existing systems and how we can measure that and how we can evaluate, how we can compare, how we can use benchmark, and based on benchmark how we can summarize the comparison. All these things were done by using some of the methodologies that was explained in the previous session. Now we'll look at some of the quantitative principles for the design of the computer system. So when we try to design a new computer system, always we will be taking the advantage of having parallelism that we can incorporate on our new system that we are going to generate. So as we know, parallelism will always increase the speed of the system, execution time can be reduced, and more response time will also be reduced, and as well as we can improve the throughput by performing more tasks within a limited given time. So it is always better to have the provision for adding parallelism when we are trying to design a new computer system. So the advantage of using parallelism is always for improving the performance of the computer system. So it is certainly being compared. We can have several examples where we can improve the performance by increasing the number of devices, or when we are implementing the parallelism into the existing system. So in order to improve the throughput performance on a server benchmark, we can use multiple processors, and by using multiple processor we can execute multiple tasks, and we can also use multiple disk for huge data processing and all. So this is one way of adding parallelism, by adding more processors and by adding more disk. So two major devices where we can incorporate parallelism is by adding more processors or by adding more disk. So these two are the more relevant and more most useful parallelism mechanisms. So if you expand the number of processors, disk and memory, we are actually improving the scalability. We can perform more operations, we can add more, we can deal with more data and from the secondary for huge data, and we can hold more operation within the primary memory, so that simultaneously we can execute a number of programs if we increase the size of the primary memory. Similarly, spreading of data across many disks for parallel reads and writes, that is called as data level parallelism. If we increase the number of disks, we can increase the data level parallelism, so that different data, so if you are having some 1 lakh number of data available, and if the data are distributed among different disks, so simultaneously we can work on some portion of the data, so that the process can take only less time to complete the entire task. Then for an individual processor, for increasing the parallelism, we are using the concept called as pipelining, where we need to use the same processor, but for one particular operation we need to divide the task into separate stages, and each stage can be executed in parallel by using the mechanism called as pipelining. Now The basic idea behind parallelism is to overlap instruction execution to reduce the total time to complete an instruction sequence. So that is the idea behind parallelism, and especially the idea behind the pipelining. We can overlap the instructions. So if we are having some 5 instructions are to be executed, now one instruction, if one instruction is doing one operation, the second instruction can utilize some other area. Sometimes it can utilize the memory, sometimes it can utilize the CPU, sometimes it can utilize the IO. So if that is being arranged properly within the time duration, so that we can reduce the total time taken to complete these set of instructions to be completed. We can improve the parallelism. So pipelining is an example that uses instruction level parallelism, so that different instruction stages can be formed, and each stage of different instruction can be simultaneously working. That implements the concept of parallelism. Parallelism can also be exploited at the level of detailed digital design. So in the IC side also, if it adds more processor in the multiple cores being incorporated within the system, there also we can improve the parallelism, so that we can perform more than one task simultaneously. Then another mechanism is to use the concept of caches, that is set associative caches that uses banks of memory. So in relation with the internal processor, if they add some more banks of memory as a cache memory closer to the system, every time the system will be looking into the cache for accessing the data, so that it can easily get the data and perform the data, and that will increase the speed of the entire execution. So that is also an enhancement for improving parallelism by adding cache memories into the computer system. Most modern ALUs use carry look ahead, which uses parallelism to spread the process of computing sums from linear to logarithmic in the number of bits per second. So most ALUs, for inner to parallelize the arithmetic logic unit operation, they are using carry look ahead buffer like structure, where they can perform the parallelism on the computing summation, etc., on various type of numbers used in the computer system. So ALUs are also made in such a way that they can parallelize the computation that is to be performed by the system. Principle of locality. Principle of locality is the basic concept behind the usage of cache memory. Let us see what is principle of locality. Programs tend to reuse data. So whichever data that is to be used once again, or whichever data that we were using recently, we always have the tendency to access those data. Most frequently used data or most recently used data. These two data mostly they require again and again when we are working, or when some program is being executed within the computer system. So that property is called as principle of locality. So we are focusing on that local recently used data and the data that is available very closer to the processor. An implication of locality is that we can predict with reasonable accuracy that instructions and data a program will use in the near future based on the access to the recent past. So most of the time we can assume that we are assuming that a program always requires the data in the near future which was recently being accessed. So based on this concept we got the principle of locality concept. So there are two types of localities from where we can easily access the data. One is temporal locality, that is based on the time. Temporal is always deals with the time, that is the recently accessed item are likely to be accessed. That is very clear. So I was using one particular data, I was sometimes when we are opening the browser, the Google will be automatically available there. It is because that Google was the most recently used web page, and it will automatically come from the cache into our browser. So temporal locality, the recently accessed item are likely to be accessed again. Similarly, spatial locality means the items whose addresses are near one. So we always, so for any operation, we always try to access the data that is very closer. So that is the reason why we need to have a place where we need to keep some data very closer to the processor. So spatial in terms of the place where the data is residing, and temporal in terms of the time recently, or which time the data was used as part of our processing. So all these provides this principle of locality is actually gives a mechanism, or we can have a better performance by increasing the speed of the entire program execution in a computer system. Now focus on the common case. Now we are going to discuss about a different situation. In making a design trade-off, favor the frequent case over the infrequent case. So when we are working on a system, some portions are being executed very frequently and some modules are executing very rarely. So we have to consider two things. Some instructions are used very frequently and some instructions are used very rarely. So we have to have a comparison between these two. This is frequently used and this is rarely used. So every time, in order to increase the speed or parallelism of the system, we need to focus on the common case. Which is the common case? Common case is the frequently used item, not the rarely used item. So we need to always focus on the common case, which is the very frequently. So if you apply some parallelism on the frequently used item, we can have some betterment added into the execution of the whatever process we are doing. Similarly, if we are trying to apply some enhancement on the rarely used or rarely or infrequent case, so there we won't be getting that much advantage on adding some feature on that rare or infrequent case. So we are always trying to focus or favor the frequent case rather than infrequent case. So focusing on the common case works for power as well as for resource allocation and performance. So for all these means when we allocate some resource, or if you want to improve the performance, for all these it is always better to focus on the common case than the infrequent case. So the instruction fetch and decode unit of a processor, one example is given like the instruction fetch and decode unit of a processor may be used much more frequently than a multiplier. So many instructions are executing simultaneously and all the instructions require fetch and decode, but not all the instructions require the multiplier. Multiplier is required only when a multiplication operation is to be done. So it is always better to optimize the operations that happens with the instruction fetch and decode. So just focus on the common case or frequent case that will be utilized most of the time by the so our aim is to design a new system where we need to improve the speed, improve the parallelism. So while trying to improve the parallelism, focus on the common case or the frequent case. It is always better not to focus on the infrequent case. So a frequent case is often simpler than and can be done faster than the infrequent case. So that is the general principle. Now one example is given. When adding two numbers in the processor, we can expect overflow to be a rare case. So when we are trying to add two numbers, some situation when we try to add two numbers, not in all situations we will be having overflows. but only rarely we'll be having a chance of having overflow when we are adding two numbers. And we can therefore improve performance by optimizing the more common case of no overflow. So we will try to, so we will be having some situation where there is no overflow, and there are some situation when we are having overflow. So overflow happens very less frequently only, and no overflow is the most frequently case. So we try to improve the performance of this area where we are having no overflow happens. One example is, general example is given for a simple arithmetic operation. So this emphasis may show down the case when overflow occurs, but if that is rare, then overall performance will be improved by optimizing the normal case. So if some problem happens with overflow, then also no problem, it will take some time on this overflow situation, but it happens only very rarely. So that is why it won't be affecting that much on the entire performance. But if something extra being applied to the no overflow area and some parallelism or some enhancement being added into this particular area, so it always happens. Most of the time this area will be working, so it can affect the entire, or it may add advantage to the entire working of the program execution. So we have to decide what the frequent case is and how much performance can be improved by making the case faster. So we have to decide what is the frequent case. So we need to identify, we have to filter the most frequent case and infrequent case, and while a designer tries to develop a new system, they need to add some enhancement. So he need to find out which is the frequent case and which is the infrequent case. Just try to avoid infrequent case and try to add enhancement, or focus more on adding enhancement to the frequent case, so that we can have an effect, a better effect of performance improvement on the entire system when we are working on the newly developed system. So we are using a law that is called as AMDAHL'S law, which is used to quantify this principle. So in a computer system, when we develop a new system, we need to filter two areas. One is the frequently used areas, and second one is not frequently used areas. So find out those areas and add enhancement to the frequently used area. So it is being applied by using, so that enhancement we are adding a feature by applying the law defined by AMDAHL, which is called as AMDAHL'S law. So what is the principle here? Focus more on the common case is the principle. Based on that, we are having a law called as AMDAHL'S law. Now, what is AMDAHL'S law? Just look in detail. This is a very, very important portion as far as computer architecture is concerned. The performance gain that can be obtained by improving some portion of a computer can be calculated using AMDAHL'S law. The performance gain that can be obtained by improving some portion of a computer can be calculated using AMDAHL'S law. So as I have mentioned, this is the entire computer. Several portions are there for the execution. So performance gain, so there will be some performance based on the normal flow by improving some portion. So I am trying to improve this portion. For this portion I am giving some improvement. That means maybe I will be adding some parallelism, maybe I will be adding one more redundant device, some enhancement to be added into a particular portion of the computer. Now what will be the performance gain? So we need to quantify this. Okay, so this is the, for example, this is the entire computer which is having the input device, which is having a CPU, which is having a memory, which is having an output. So in the CPU I am going to give some enhancement. This is only an example, but internally we are having several sub devices available. So there we need to consider those devices or the units that are very frequently used, and on those area we need to add some enhancement. So we need to consider only the common case or frequent case. There we need to have some enhancement. Enhancement in the sense adding some parallelism or improving the performance by applying something on that, so that the entire speed can be improved. So we can the performance gain can be evaluated. So for example, the normal system, if it is working normally, it takes, I'll take the performance is 10, and if we are improving this area, the performance is for example improved to 20. I am simply giving two values just for understanding. Normal flow, the execution is performance is 10, and when we improve some portion of the entire computer system, the performance has been improved to 20. So now we can see that the performance gain is 2 times 10 to 2, that is 20. 2 times is the performance gain when compared to the previous normal flow of execution. So in order to find out this performance gain, we are using the quantitative principle that is called as AMDAHL'S law. So this is the AMDAHL'S law. It's a very important point, how to define AMDAHL'S law. AMDAHL'S law states that the performance improvement to be gained from using some faster mode of execution, that means by enhancing this area, is limited by the fraction of the time, the faster mode can be used. Once again, AMDAHL'S law states that the performance improvement to be gained, overall improvement to be gained from using some faster mode of execution is limited by the fraction of the time, the faster mode can be used. So we are only considering some performance gain for the entire system by applying some additional enhancement to some particular area. Accordingly, we will be having some speed up, some gain is being obtained. So this law actually defines. So this is the statement, theoretical statement of AMDAHL'S law. But according to the law, we need to define speed up. That is the gain. Speed up is the gain due to the performance improvement. So speed up can be defined as performance for entire task using the enhancement when possible. So on top we are having with enhancement. What is the, for example, 20 was the value here, right? With enhancement the performance was 20, and downside the performance for the entire task without using the enhancement, that is 10. Speed up is equal to the performance due to the enhancement divided by the performance without enhancement. Now we are getting the value as 2. What is the speed up now? Speed up is 2. That is the speed up. Alternately, when we compare that to means performance to be converted to execution time, the speed up can also be defined as execution time for the entire task without using the enhancement. That will be the reverse of this one. Execution time to the task without using enhancement to the execution time for the entire task using the enhancement when possible. So execution time of the task with enhancement comes in the downside. Okay, so speed up in terms of performance and speed up in terms of execution time. So the performance gain due to some enhancement added into some portion of the computer system. So where we are giving enhancement? We are giving enhancement to the common case, frequent case, so that the gain can be improved. If we apply this enhancement on a rare case, it won't be affecting that on the entire performance. So there won't be that much performance gain. It is always better to choose the common case or frequent case where we can apply the enhancement, and accordingly we can have more performance gain due to the enhancement applied to the portion of the computer system. So this is the theoretical definition of AMDAHL'S law, and the law defines speed up. So we need to identify the speed up in terms of performance and in terms of execution time. So it gives, AMDAHL'S law gives us a quick way to find the speed up from some enhancement which depends on two factors. So that's what we were mentioning in the previous slide. The fraction of the computation time in the original computer, that can be converted to take advantage of the enhancement. So the enhancement is depending on the fraction of the time where the enhancement happens. The time variation, the fraction of the computation time in the original computer that can be converted to take advantage of the enhancement. So the time taken before adding enhancement and the time taken before adding enhancement, that is to be compared. So we'll be having some better time, computation time. Better computation time means the enhanced area will take only less time for the completion of the computation. For example, if 20 seconds of the execution time of a program that takes 60 seconds in total can use an enhancement, the fraction is 20 divided by 60. If 20 seconds of the execution time of a program that takes 60 seconds in total can use an enhancement, the fraction is 20 divided by 60. That is called as fraction enhancement, which is always less than or equal to 1. That enhancement, so out of 20 seconds we are giving enhancement out of 60, then this value will always be a value that is less than or equal to 1. If 20 seconds of the execution time of a program that takes 60 seconds in total can use an enhancement, so this is the total 60 seconds. Out of this 20 seconds we are doing enhancement, remaining 40. So out of 60, 20% we are, so 20 is the takes the enhancement, and in total 60. 20 by 60 is the fraction that is being enhanced. The fraction enhancement is evaluated by using this concept. Okay, so I hope it is clear. We will see some problems and some examples also. The improvement the improvement gained by the enhanced execution mode, that is how much faster the task would run if the enhanced mode were used for the entire program. The improvement gained by the enhanced execution mode, that is how much faster. So automatically some portion of the entire task will be given some improvement, so that automatically the entire program, the performance gain will also be improved. So this value is the time of the original mode over the time of the enhanced mode. Before the enhancement what was the time taken, and after the enhancement what is the time taken. So that will be varying. So if the enhanced mode takes 2 seconds for a portion of the program, while it is 5 seconds in the original mode. So an entire program, if we are not having enhancement, it takes 5 seconds. But if you are having enhancement, it takes only 2 seconds. Okay, then the improvement will be 5 by 2. As I was mentioning in the previous case, that is about the fraction of enhancement. Out of 60, 20 portions. So the fraction that is being enhanced is 20 by 60. So out of 60, 20%. 20 second, for example 20 second is the enhancement. So fraction, how many fraction that is given enhancement is 20 out of 60, that is 20 divided by 60, which is less than or equal to 1. So we need to consider when we take several problems. And now we have to consider one more point, that is the without enhancement the total time taken for completing the task was 5, for example, and after enhancement the time is reduced to 2. Then we can take the improvement or evaluate the improvement as 5 divided by 2, which is greater than 1, always greater than 1, and this is called as speed up enhanced. So we have considered 2 points. One is fraction enhanced, total area, total time, in that how many fraction, which area we are giving enhancement. So that particular area divided by the total available, that decides the fraction enhanced, which is always less than or equal to 1. That is to be remembered. Second point is, if you reduce the time from 6 to 2, for example, or from 10 to 5, whatever it be, the original time was 10, after enhancement the time became 5. So how we can calculate the speed up enhancement or speed up enhanced? That is 10 divided by 5, that is 2, or in this case it is 5 divided by 2, which is a value that is greater than 1. Always it is around 2.5. Okay, so we need to use these 2 factors for applying the AMDAHL'S law formula, fraction enhanced. So we must understand what is fraction enhanced and what is speed up enhanced. So accordingly, the execution time using the original computer with the enhanced mode will be the time spent using the unenhanced portion of the computer plus the time spent using the enhancement. So now the execution time of the new system can be evaluated as, so this is the formula that we are going to focus when we apply some when we work on some problem. The execution time of the new system can be calculated as the execution time of old into 1 minus fraction enhanced. So this fraction enhanced is always a value that is less than 1. So 1 minus that fraction enhanced plus fraction enhanced, same value, divided by speed up enhanced. We already know what is execution time of old. We know what is fraction enhanced. Then we know what is speed up enhanced. So that we can find out the execution time of the new system. What is the new system? New system means the new system or the system after adding the enhancement. Now the overall speed up. So first of all we need to find out the execution time. If you want to find out the execution time of a new system and compare to the old system, we can apply this formula by using AMDAHL'S law. Similarly, the overall speed up can also be evaluated, that is by taking the ratio of the execution time of both old and new system. The overall speed up can be evaluated as execution time of old to the execution time of new, which is equivalent to 1 divided by 1 minus fraction enhanced plus fraction enhanced divided by speed up enhanced. Okay, so speed up overall can be evaluated as execution time of old to the execution time of new, which is equivalent to, in terms of performance, 1 divided by 1 minus fraction enhanced plus fraction enhanced divided by speed up enhanced. So just look at this speed up. So based on this speed up, we are taking the overall speed up, performance from enhanced to without enhancement, and alternately speed up. Okay, so this is the two way of finding the speed up. So speed up in terms of execution time is given as the second one. So from there we have evaluated this formula, speed up overall, that is execution time of old to execution time of new. After evaluating this execution time of old to execution time of new based on the previous formula, we'll get the final overall speed up as 1 divided by 1 minus fraction enhanced plus fraction enhanced to speed up enhanced. So what will be the derivation? You have to remember 2 points. First thing is, according to the AMDAHL'S law, what is the execution time of a new system, which is equivalent to execution time of old into 1 minus fraction enhanced plus fraction enhanced divided by speed up enhanced. What is the overall speed up? So most of the problems they will be asking to find out the execution time and to find out the overall speed up. So overall speed up is equivalent to 1 divided by 1 minus fraction enhanced plus fraction enhanced divided by speed up enhanced. What about fraction enhanced? Fraction enhanced is total time, out of which how much fraction that divided by the total time. What is speed up enhanced? Speed of the old, speed of the new. The speed of new, speed of the old divided by speed of the new. We'll get the speed up ratio. So based on this, we can substitute the values on this formula and we can find out the overall speed up of the. So these are the two quantitative measures being evaluated based on AMDAHL'S law to get the enhancement, or when we design a new system, when some enhancement is being added, we need to say that this is having a better execution time than the previous one. Also we should have an idea about, we should mention that the overall speed up gained by using this system is better than the previous one. So one example is given. Just look at this. So just remember the previous formulas. Suppose that we want to enhance the processor used for web serving. Okay, we want to enhance the processor. The new processor is 10 times faster on computation in the web serving application than the original processor. The new processor is 10 times faster. Okay, just remember this, it is 10 times faster on the computation in the web serving application than the original processor. Assume that the original processor is busy with computation 40% of the time and is waiting for I/O 60% of the time. So it is working 40% of time the processor is busy, and 60% of time it is waiting for I/O. It is idle actually. Okay, so what is the overall speed up gained by incorporating the enhancement? So the fraction enhanced. What is fraction enhanced? Fraction enhanced. So out of 100% time, 40% of the time it is using processor. So fraction enhanced is 0.4. That is to be enhanced. Other 60% of time it is waiting for I/O. We don't need to do anything on that. So 40% of the time it is busy with computation. In that 40% of time we are going to add enhancement. So the fraction is 0.4. Now the speed up enhanced is equivalent to, see, the new system is processor is 10 times faster. It is already given. The speed up enhanced is already 10. It is 10 times faster. Now what is the speed up of overall? So now we can simply evaluate speed up overall is equal to 1 divided by what is that, 0.6 plus 0.4 divided by 10. Okay, so just look at the formula once again. In the previous slide we will see the formula once again. The overall speed up can be evaluated as 1 divided by speed up overall 1 divided by 1 minus fraction enhanced 1 minus fraction enhanced 1 minus 0.4, that is 0.6. It's correct, don't confuse. 1 minus fraction enhanced is 0.4, that is 1 minus 0.4 we are getting 0.6 plus fraction enhanced, that is 0.4 again here, divided by speed up enhanced, that is 10. Then after evaluating this formula we will be getting 1 divided by 0.64, which is equivalent to 1.56. So by adding an enhancement to the 40% of the time which is busy with CPU, we are adding some enhancement. There will be an overall speed up of 1.56. So the new processor is actually 10 times faster. So enhancement is added to the processor. Enhancement is added to the processor. Enhancement is added to the processor. That is 40% of the time it is utilizing CPU, and that CPU is enhanced 10 times. Speed up enhanced for that particular device CPU is 10 times. So for the entire system, only for CPU, that is 40% of the time CPU is being enhanced, 10 times speed up is being maintained. So automatically the entire system is having an overall speed up of 1.56. I hope it is clear. So the AMDAHL'S law is particularly useful for comparing the overall system performance of two alternatives. So we can have a comparison between two systems. When we compare two systems, we can compare the overall speed up that is being gained. So we can have a comparison. So this can be applied for comparing the performance of overall performance of two different alternative systems. It can also be applied to compare two processor design alternatives, two processor design. So one processor is designed by adding some enhancement on some portion. Some other processor is designed by adding some enhancement to some other portion of the processor. So we can have a comparison between these two, and which can be selected accordingly by comparing these two processor design, whichever being having better execution time or whichever being having a better speed up, overall speed up, that can be selected as a, or that can be considered for the design of a new computer system. Now we look at one more program. A common transformation. The problem is given in a very large format, but it's also a very simple program. A common transformation required in graphics processors is square root. One of the common operation in a graphics processor is square root. Implementations of floating point square root vary significantly in performance. So square root on floating point values. Okay, so I am underlying only those important portions, especially among processors designed for graphics. Okay, so floating point square root is a very crucial operation in that. Suppose floating point square root is responsible for 20% of the execution time. Okay, on overall 100%, 20% of the time it is focusing on floating point square root operation, this operation. of a critical graphics benchmark. One proposal is to enhance the floating point square root hardware and speed up this operation by a factor of 10. So one proposal is given that it will be 10 times improved by adding some enhancement on FPSQR. So remember, FPSQR is utilizing 20% of the total execution time. So the fraction enhanced is always that is clear. Okay, that is 0.2. That is clear from here itself. So when we get all values, we can write it down. Fraction enhanced is 0.2. Now, what is the speed up? If we improve this FP square root hardware, that is 10. Speed up enhanced is equal to 10. So you can write step by step. The other alternative is just try to make all FP instructions in the. So this is one alternative. Fraction enhanced is 0.2 and the speed up enhanced is 10. The other alternative is, so we are going to compare two systems. So this is one enhancement. Now the other alternative is just to try to make all FP instructions in the graphics processor run faster by a factor of 1.6. So all the floating point instructions in the graphics processor, here we are considering only improving floating point square root operation. Here it is considering by improving all the floating point instructions in the graphics processor run faster by a factor of 1.6. So all the FP instructions must be enhanced by adding some enhancement. So the FP instructions are responsible for half of the execution time for the application. So 50% of the time. So for the second alternative, also the values are given. Speed up enhanced is 1.6 and half of the execution time, that is 50% of the execution time, that is the fraction enhanced is 0.5. Okay, so first case fraction enhanced is equal to 0.2. We'll just write these values. Then speed up enhanced is 10. That is for the first case. Okay, that is for. Then for second case, fraction enhanced is, everything is given directly in the problem. Fraction enhanced is half, that is 0.5, and the speed up enhanced is equal to, that is 1.6. We'll just substitute the value on the formula. So the design team believes that they can make all FP instructions run 1.6 times faster with the same effort as required for the fast square root. Compare these two design alternative and just have a comparison on which is better. Okay, so one situation, adding enhancement to only floating point square root hardware. Okay, just adding enhancement to only the floating point square root hardware. Second is adding enhancement to all the FP instructions. But only adding FP square root hardware, it is having a speed up of 10. But adding all the FP instructions, speed up will be only 1.6. Okay, we'll have a comparison. So speed up of a system that uses FPSQR is equal to speed up due to adding enhancement on FPSQR equal to 1 divided by 1 minus fraction enhanced is 0.2 plus fraction enhanced 0.2 divided by speed up enhanced is 10, which is equivalent to 1 divided by 0.82, which is equivalent to 1.22. Now second case, so these values are substituted here. Now for second case, speed up due to improvement added to all the FP instructions equal to 1 divided by 1 minus fraction enhanced is 0.5 plus fraction enhanced 0.5 divided by speed up enhanced is 1.6, which is equivalent to 1 divided by 0.8125, which is equivalent to 1.23. Okay, so when we take what is the result of these two? We are getting a very nearly value 1.22 and 1.23. Improving the performance of the FP operations overall is slightly better because of the higher frequency. Okay, so two design aspects. When a designer tries to design a new system, one alternative, he is thinking about improving FP square root hardware. Second, he is thinking improving all the FP insertion, some enhancement being added into that. So how we can assess which one will be better? So he is applying the AMDAHL'S law, and based on all these constraints, and among these, by applying these two, they are getting the speed up on both these situations. Accordingly, he is finding this speed up due to the enhancement on all the FP insertion is slightly better than this one. 1.23 is better than 1.22. So AMDAHL'S law can be applied for comparing the design alternatives of two different computer systems. Next comes the processor performance equation. The processor performance equation. So all computers are constructed using a clock running at a constant rate. You know, the speed of the computer is decided by the clock speed of the computer system. So the clock, even the time can be considered in terms of, sometimes it is called as ticks. It can be called as clock ticks, clock periods, clocks, clock cycles, or clock cycles. It is named in different formats. So time of a clock can be referred by its duration. So performance is usually in this explanation we are going to discuss in terms of speed of the processor. That means clock speed, based on the clock, how we can evaluate the performance of the system. So time of a clock can be referred by its duration. For example, the measures can be taken like 1 nanosecond, or by its rate like 1 gigahertz. Most of the processors are known by using the clock speed in terms of gigahertz. Now, but 1 nanosecond is cycles per instruction only, means cycles per second. So that decides the base time. That is the base time of the or clock cycle time. Like in our clock, second is the base. From the second only we are forming minutes, and from minutes we are forming hours. Similarly, the base measurement is 1 nanosecond for the case of a clock. So two ways to represent CPU time of a program. CPU time is equivalent to the CPU clock cycles for a program into clock cycle time. CPU time can be evaluated by using CPU clock cycles for a program. So for a program, it takes some, for a program to be executed, it takes some 100 clock cycles, for example. For a program. Into, so one program is executing now within CPU, that program takes 100 clock cycles, into clock cycle time. Clock cycle time is, for example, 1 nanosecond. So 100 into 1. So CPU time will be 100 nanosecond. CPU time can be evaluated by using this formula. Similarly, it can also be evaluated by using another formula, CPU clock cycles for a program to the clock rate. CPU clock cycles for a program. So 100 to the clock rate. So clock rate will be varying. Okay, so clock rate will be varying accordingly, so that we can decide the CPU time of the computer system. In addition to the clock cycles needed to execute a program, we also count the number of instructions executed, that is called as the instruction count. So previous case we were considering only the total cycles for a program. So it also depends on the number of instructions also. So the number of instructions that are executed within a CPU will also be considered. Also, we can calculate the average number of clock cycles per instruction. Cycles per instruction. So, in order to calculate this, we need to find out cycles per instruction. So, if you are having 10 instructions available, so how many cycles per instruction? So, this is one instruction, second instruction, third instruction. So, that decides the number of instruction, that is instruction count. Now for each instruction we will be having how many cycles. For first instruction, how many cycles? For second instruction, how many cycles? For third instruction, how many cycles? So totally how many cycles per instructions are available. So number of instructions vary in different situations. So the total cycles per instruction can be evaluated as CPU clock cycles for a program. The total CPU clock cycles for a program divided by the instruction count will get the average cycles per instruction. So if you are having some 10 instruction available, the total CPU clock cycle for that particular program divided by 10 will give the cycles per instruction, that is an average value. An average cycles per instruction is taken for completing that particular program. Now by transposing the instruction count in the above formula, CPU clock cycles for a program is equivalent to CPI into instruction count. So the same formula is converted into this format. CPI is equal to CPU clock cycle to instruction count is being transposed. Now the CPU clock cycles for a program, total CPU clock cycle for a program is equivalent to cycles per instruction into instruction count. So all these are used for processor performance evaluations. Now CPU time is equivalent to the total CPU time can be again equivalent to instruction count into, so before we were discussing about cycles per instruction into clock cycle time. Now we are adding the instruction count also. So total number of instruction into cycles per instruction into clock cycle time, that is the total CPU time. Now by expanding this instructions per program, that is instruction count, into clock cycles per instruction, that is cycles per instruction, into clock cycle time, that is seconds per clock cycle, which is equivalent to second by program. So this instruction will get cut off, clock cycle will cut off, then seconds per program, which is equivalent to the CPU time, the number of seconds per the entire program. Okay, so that is how we can evaluate the CPU time usage of the. So why we are finding out the CPU time is to have a comparison, because when we work on different programs, we can decide the capability of the CPU by checking various programs and comparing the CPU time. And how we need to find out the CPU time based on the values that depends on the program, the number of instructions, the cycles per instruction, and the basic clock cycle time. The processor performance and CPU time depends on clock cycle as per the previous formula. The performance and CPU time depends on clock cycle, the cycles per instruction and instruction count. Now a 10% improvement in any one of these leads to a 10% improvement in CPU time. So here also, if you are applying the previous AMDAHL'S law like structure, if we improve any of so clock cycle into CPI into IC is the formula for finding the CPU time. If you improve the clock cycle, or if you improve the cycles per instruction, or if you improve the instruction count, which leads to some improvement in the overall CPU time also. So clock cycle depends on hardware technology. So when we consider these three, clock cycle is depending on hardware technology and organization. Accordingly, so that cannot be easily done. A new hardware can be implemented where we can improve the clock cycle. Then cycles per insertion depends on the organization and insertion set architecture. It depends on the insertion format and all, insertion set architecture and all, the cycles per instruction. So how many cycles it will take, it is depending on the length of the insertion and all. So the CPA will be affected based on the functional organization as well as the insertion set architecture in terms of insertion length and the complication of the insertion. Now insertion count depends on the insertion set architecture and the compiler technology. So how many insertions will be available? First thing is depends on the insertion format, and second thing is some compilers, when they do optimization and all, they will reduce the number of insertions. So it depends on the compiler technology whether the insertion count will be increased or decreased. That will be depending on these two factors. So if you make any change on any of these parameters, it will affect the overall CPU time. So these three things are varying, depends on clock cycle depends on hardware and organization, CPA depends on organization and ISA, IC depends on ISA and compiler technology. Now the processor performance equation. The number of total, the continuation of the previous thing, the number of total processor clock cycle can be calculated as total processor clock cycles. So CPU clock cycles can be evaluated as the summation of 1 to n IC insertion count into cycles per insertion. So IC I indicates number of times insertion I is executed. So some insertions will be executing some 5 times, some insertion will be executing 4 times, some insertion 2 times. That depends on the program. So the total CPU clock cycles can be evaluated by using this formula by taking the summation of IC insertion count into cycles per insertion for each insertion. That is why we are having I from 1 to n. So n insertion, so first insertion its count, second insertion its count, so that much time that will be multiplied for each cases. So for each insertion this entire summation will be evaluated. Now this is the way in which we are finding out the total CPU clock cycles required for a program for the processor. Now CPU time can be evaluated as the same thing, total processor CPU clock cycles into clock cycle time. Okay, so that was the formula there, right? Insertion count into cycles per insertion into clock cycle time. So when it comes to the entire CPU time, total CPU time for all the programs, for all the insertions, so the summation of all the insertions and its count will be taken, and the clock cycle time will be multiplied with that, will be getting the overall CPU time. Now overall CPI can be given as insertion count into cycles per insertion divided by the total number of insertions. So total number of insertion to each insertion, how many times it is there, each insertion cycles per insertion to the total number of insertions available in the entire system, which is equivalent to sigma equal to 1 to n insertion count divided by insertion count into CPI3. The same thing is rewritten in this particular format. So several situations we have to find out. So every time when we evaluate the processor performance, it is strictly based on the CPU time. So CPU time is depending on the insertion count, cycles per insertion and clock cycle time. So it can be evaluated based on the single program, or can be based on the entire processor, entire operation, by taking all the insertion count and its individual number of times each insertion present into the cycles per insertion and the clock cycle time. So we will look at some more example problems related to AMDAHL'S law as an exercise. So what is the overall speed up if you make, so this is the solution for the first one. Once again, AMDAHL'S law, speed up is equal to 1 divided by 1 minus fraction enhanced plus fraction enhanced divided by speed up enhanced. It's a very important formula. So what is the overall speed up if you make 10% of a program 90 times faster? Okay, so this is the first program. 1 divided by 10% of the fraction enhanced is 0.1. 1 minus 0.1 plus 0.1 divided by 90 times faster. So speed up enhanced is 90. It is equivalent to 1 divided by 0.9011, 1.11. Okay, it's very simple. All the values are directly given. Then for the second program, what is the overall speed up if you make 90% of a program 10 times faster? The opposite of this one. Opposite of this one. What is the difference here? 1 divided by 1 minus 0.9, that is the fraction here, plus 0.9 divided by 10, which is 1 divided by 0.19, which is equivalent to 5.26. Okay, so here it is more faster than more speed up is being overall speed up is being improved on the second situation. So these are two different programs only, two different problems only, but this is having a better speed up when compared to the previous case. One more example in relation with the AMDAHL'S law. We are considering an enhancement to the processor of a web server. The new CPU is 20 times faster on search queries than the old processor. Okay, so the new CPU is 20 times. So speed up enhanced is 20. Just remember that speed up enhanced is 20. That is already written here. The old processor is busy with search queries. We are considering speeding up of search operation that is utilized by CPU with search queries 70% of the time. Okay, so the fraction enhanced will be 0.70, that is 70% of the time. What is the speed of gain by integrating the enhanced CPU? Formula will be very clear. Speed up is equal to 1 divided by 1 minus fraction enhanced is 0.70 plus 0.70 divided by 20, that is the speed up enhanced, which is equivalent to 1 divided by 0.335, which is equivalent to 2.985 times. That is the speed up that is being enhanced because of the change that is applied to the earlier system. So some enhancement made some betterment in the speed up of the new system. One more example. We are considering an enhancement to the processor of a server. The new CPU is 10 times faster. So speed up enhanced is 10. Speed up enhanced is 10. Okay. It is an IO bound server. It is an IO bound server means most of the time it is focusing on IO operation. So 60% of time waiting for IO. So we are thinking about the CPU. So 60% of the time it is waiting for IO. We are thinking about enhancement of CPU. So rest 40% it is utilizing for CPU. So the fraction enhanced will be 0.4, right? So 1 divided by 1 minus 0.4 plus 0.4 divided by 10, which is equivalent to 1 divided by 0.64, which is equivalent to 1.56. So the speed up enhanced is 1.56 for this particular situation. Okay, so all these programs are actually they are following the same thing. Every from the starting itself, we are focusing on the common case. So we are focusing on a particular area where we need to have some enhancement. Now for that enhanced area, we are finding the fraction enhanced, then what the speed up gain for that particular area. Then accordingly we are trying to find out the overall speed up by using the AMDAHL'S law. Once again, the AMDAHL'S law, the speed up is calculated as 1 divided by 1 minus fraction enhanced plus uh, fraction enhanced divided by speed up enhanced. It's a very important formula that is used with the performance of the system. So that's it for now. We have in this session we have seen the quantitative principle of computer design, the importance of parallelism, adding enhancement, adding cache memory and other features, so other enhancement. And for evaluation based on enhancement, we are using a general formula which is called as AMDAHL'S law in order to find out the execution time, the performance and the speed up gain due to the enhancement. And we have also mentioned about the CPU how we can evaluate the performance of processor. That means to evaluate the total CPU time based on the insertion number of insertion count, the cycles per insertion and clock cycle time. And we have seen some example problems, very important problems related to the AMDAHL'S law, which is a very major and very crucial problems in terms of the finding of overall speed up of an enhanced computer system. So that's it for now. Thank you.